So taking a look at section 3.4, it's a section called linear programming, which is a method of finding a maximum or a minimum value given a set of conditions called constraints. This is important because it's actually a real application of what we've been doing. A lot of businesses want to maximize profit while minimizing costs. So they'll use linear programming to figure out what variables will give them what they need. The constraints are the inequalities in the linear programming problem. The feasible region, all this relates to the system of inequalities we just solved. That was kind of a generic example. And like I said, now we're going to be looking at word problem examples. The feasible region is the solution. So that's where the shading would overlap, thinking back to what we did in the last section. The objective function is the function that you want to maximize or minimize. I know this is a lot of information being thrown at you and you may not understand all of it, but as we go through the lesson, I'll use these vocab terms so that you can kind of understand where they tie in to what we're doing. And finally, the vertex principle, and this is essential for what we're doing. This says that a maximum or a minimum will always occur at the vertex of a feasible region. This is important because it means we don't have to check every single ordered pair within that solution, which would be endless because of the fact that we have decimals and fractions that are also part of our region. So we only have to look at the vertices of our region to find where the max or min will occur, which saves us a ton of time. So let's start to look at this. First of all, we'll look at it without context, and then tomorrow we'll look at word problems, and then we have to set up our own system of inequalities. So the first thing we're going to do is graph the feasible region. This is where the kind of inequalities overlap. It's the shaded area that makes all of the inequalities true. So we're going to start with x is greater than or equal to 0. And since that is a black line, it's actually already my y-axis. So we'll go ahead and regraph that. Y is greater than or equal to 0. That's my x-axis. In a lot of real-life word problems, as we've already seen, the x and y-axis are our boundaries because you can't buy a negative amount of materials, for example. All right, so our red inequality, I'm going to graph using the intercepts. I'm going to take 600 divided by 1.2 to get my x-intercept of 500. And I think I'm going to scale my graph by 50s, maybe 25. All right, so my red x-intercept is at 500. 600 divided by 2, of course, gives us 300. So I'm going to go ahead and scale my other axis. And that would be 300. And this is an or equal to, so I can make this a solid line. And my blue inequality, my intercepts are both at 400. All right, so now we take a look at our shading. Obviously, we're going to be shading within the first quadrant, looking at the first two. So our second one, 0 plus 0, is less than 600. So my red inequality would be shaded towards the origin. And the same for my blue inequality. We want it less than or equal to 1,000. So we're going to shade this region right here. And for our next example, we're going to try and maximize an objective function. And thinking about that last vocab term that I gave you, a max or a min only occurs at the vertices. So we're going to go ahead and grab the vertices from this graph before we move on. So taking a look right here at 0, 300. Here at 0, 0. Over here at 400, 0. And then here, and since my graph isn't precise, I'm not sure exactly where that vertex is. So I'm actually going to solve the system in order to figure out where that vertex occurs. Which means I can solve by substitution or elimination. And I'm kind of liking elimination on this one because both the x and y's are already on one side of the inequality. What I am going to do is go ahead and solve this system off camera, so to speak, and get you the solution so that you're not wasting time going over a process that you already know, solving a system by elimination.